Okay. All right, so to find our values here for x, how do we do this? Yeah, -2 plus h, -1 plus h, 1 plus h, and then 2 plus h. Right? How do we find the y values? Yeah, we'll just use our calculator and plug those values in. So I have 3 times. Got to be careful here. We got to make sure that 2/3 is in a parenthesis. If you didn't do that, that's likely why you're getting some funky stuff. So I get 0.75. And when I make it -2, I get -1.25. And I get -1. Let's write those down here real quick. Okay. And then get those last couple in there. And then my last one. Okay. Everybody okay there? All right, let's draw our graph then. First thing I'm going to do is draw in my asymptote. Remember, my horizontal asymptote's at y equals -6. So I'm just going to draw a horizontal line that goes through -6. Got to have that in there for me to count these as completely correct. Now I'm going to plot my points. So I have -3 and 0.75. And then -2 and -1.5, -1 and -3, 0 and -4, and 1 and -4.6. So it's going to look kind of like that. Okay. And lastly, I need the domain and range. The domain for all exponentials is -infinity to +infinity. The range depends on our values for a and k. Since the a value is positive, I know we're going from k to +infinity. So k was -6 to +infinity. Let's do one more. So someone have another one that they want to look at? We'll do one more of these before we move on. Dan?
Number
2. Great. Can you read me the equation?
So it's y equals
Fantastic. Thank you. All right. Values for A, B, H, and K are -1, 0.5, -3, 4. Excellent. Next thing up, is this growth or decay? Decay. Why? Because the B value is less than 1. Good. All right. Next after that is the horizontal asymptote. So that's going to be y equals what? 4, which is the value for k. Excellent. We'll make our xy table. So I'm going to have -2 plus h, that gives me -5, and then so on. And then to find the y coordinates, I'll just use my calculator here and plug in those values. So again, I'm going to make sure I use a parenthesis here. I guess I don't really need it for this one. I guess it would be fine without it, but I'm going to put it in anyways. Okay. So when I do that, I get 0 for the first y. And then I get 2. And then I get 3. So let's write those down real quick. 0, 2, 3. Then I get 3.5. And then I get 3.75. Dan, so far so good? So next up is graphing. So let's draw our graph here. One, 2, 3, 4, 5, and 1, 2, 3, 4. I'll draw in my horizontal asymptote first, so that's going to be a horizontal line that passes through 4 on the y-axis. There's that. And we'll plot our points. So -5, 0, -4, 2, -3, 3, -2, 3.5, and -1, 3.75. So there's that. Should look something like this. Last things to do is the domain and range. The domain is easy. It's always -infinity, +infinity for exponential functions. The range depends on a and k. Since the a value is negative, we start with -infinity, and then we end with k. Are we all okay with this? Feel a bit better after running through a couple of these? Overall, this should be relatively easy. There's not a whole lot to do here, right? If you're able to plug stuff into the function and get some values out of that and know how to find the different parts, it's easy to find the parts. You just have to remember how to do it, right? Okay. Okay. So the next topic we're going to talk about are some applications of exponential functions. So today I'm going to introduce to you guys two exponential models. The first one is kind of the general exponential growth or decay model. That is y equals a times 1 plus r to the t. In this case, y is equal to some future value or amount. A is going to be our beginning or present value. R is the rate of change. Critical that we're writing that, though, as a decimal. And t is the amount of time elapsed. Typically, we're going to represent that in years. But it should be clear based on the rate of change what the unit should be there. So that's the first equation that we'll use. The second equation that we might use is called the compound interest formula. In this case, FV stands for the future value. PV would be the present value. R is the interest rate, again written as a decimal. N is the number of compounds per year. And T is the number of years. So what we're going to be doing today is we're going to be looking at some examples of like story problem situations where we can describe that situation using one of these two exponential models, and then we can manipulate those exponential models to answer questions about that story problem. Okay? So let's look at some examples here. So our situation that we're going to work with is in 1996, there were 2,573 computer viruses. During the next 7 years, the number of viruses increased by 92% each year. So I'm going to ask now a series of questions kind of about this situation. So here it says, write an exponential model giving the number of viruses n, t years after 1996. So we have two exponential models to choose from, the general model and then the compound interest model. Does this question have anything to do with banking? No, right? So the compound interest model is not the one we want. We're going to use the first one. That's basically all we need to do to tell. Okay. So let's go back and look at what each one of these letters represents in this model. So if I go back and I look at the compound interest, or I'm sorry, the exponential growth or decay model, what does Y represent? The future value. So what is going to be the future value in this situation? Great. And what symbol do they tell us to use there? N. So I'm going to replace Y with N. Just because I'm following the directions. Everybody okay with that? Okay. What does the A represent? The beginning value. What's the beginning value in this case? Great. The initial amount of computer viruses we have, which was 2,573. Okay. The next letter is R. What does R represent? The rate of change. So in this problem, what is the rate of change? 92%, but writing that as a decimal, it needs to be written as 0.92. Good. And then what does T represent? Time. So in this case, they're telling us to use T for time, so there's T. When we write an exponential model like this, we should have two letters in it, always. Okay? My next question I'll ask is how many viruses were there in 2003? What is it asking for in this question? It's asking for a future value, right? In what year is this problem taking place? It's starting in 1996, right? And then it's asking us about it some time in the future. So what we're looking for is our value for n, right? This is what we're looking for in our model. Everybody agree with that? To find n, what are we going to need to know? T. Great. So what is T going to be? Why 7? Great. So the problem says T is the number of years after 1996. And if I look at 2003, that is 7 years after 1996. So I'm going to plug 7 in for T, and then I'm going to type this into my calculator. So I get 484. We should round that to 485. Why did I round to the nearest integer here, or the nearest whole number? Yeah, a computer virus is a discrete object. You can't have a part of a computer virus. It's either all there or not all there. So rounding to the nearest whole number seems appropriate. Do you guys feel okay there? Okay. The next part, I'm going to ask to estimate when the number of computer viruses will be 125,000. So again, we'll be using our exponential model that we just created. What part of the exponential model are we looking for here? T. Why T? It's asking a when question. That's a time question, right? Everybody agree with that? So we have to be a little bit careful in our reading on these. So in order to solve for time, we're going to have to plug in a value for n. What is the future value for n in this case? 125,000. We want to know when that value would be 125,000. The present value we know is 2,573. We want to solve this equation now for t. Do we know how to do this algebraically? I don't think you do. What would you do to solve this algebraically? You shook your heads yes. I want to hear. Well, there's no adding going on, so I'm not sure I would do any subtraction here. Okay, what do you want to divide by? Okay, then what are you going to do after that? How are you going to get that variable out of the exponent? We don't know, right? Which is fine. This is one of the things that we'll address during the course of this chapter, but right now we don't have the tools to do this. So what are we going to do to solve this equation instead? We're not going to leave it like that. We have enough to solve this. We just can't do it algebraically. So what I'm going to do is, instead of thinking about this as solving one equation, I'm going to think about it as solving a system of two equations. And I'm going to solve that system of two equations graphically. That was one of the methods that we had for solving a system way back in first semester. You remember that? What does the solution of a system of two equations look like graphically? What does that graphical solution look like? It's the intersection of those two lines. Exactly right. So what I'm going to do is I'm going to graph these two equations on my calculator and use my calculator to find that point of intersection. Everybody good with that plan? So the calculator is going to do all the heavy lifting for me here. All I have to do is get it set up. So we want to graph. So what button do we press on our calculator if we want to graph something? Good. We go to the y equals button. And if I have anything in here, I'm going to clear that stuff out. If you guys have your calculators with you and you would like to follow along, I invite you to do that. If you just like to sit and watch, that's fine. But when it comes time to do the homework, I might cue up this part of the video and watch this again just so you refamiliarize yourself with the buttons that you have to press to get to these menus and stuff, particularly if you can't remember. Okay, so we pressed the y equals button. We cleared out any equations that might have been in there already. There's one other thing that I want to do before I get going, is I want to check up here where it says plot 1, plot 2, and plot 3. Make sure none of those are highlighted. You notice that none of mine are highlighted. If one of them is highlighted, just use your arrows to move up to it and press enter to unhighlight that. It'll give you problems trying to graph it if that's the case. Okay. So let's start typing in our equation. So in place of n, I'm going to instead type the y. That's already on my calculator for me, right? It says y equals. So I'll do 2,573 times 1.92 to the, and instead of the t, I'm going to use the letter x, because when I'm graphing on my calculator, that's the variable name we have to use. Okay. And then my next equation, instead of n, again, I'm going to use y, because that's the variable in my calculator. And then I'll type 125,000. Everybody good with that? Now, if I hit graph right now, we're probably not going to see anything. What should I do before hitting graph here? Change the window. Very good. So let's press that window button right next to the y equals. So let's figure out values for the x min, x max, and y min and y max. What is our x representing in this case? T, which was time in years. So time can never be negative, right? That doesn't make a lot of sense. I don't know what negative time would mean. So let's use 0 as our x min, because it can't have less than 0 time. Everybody agree with that? Okay. What would be a good maximum value for time in this question?
60.
I would say considerably less than that. Reread the original question. 1970? How about 7? Why 7? Because it says that this pattern that's going on, the exponential model we built, is only good for those 7 years, right? So the biggest value for t we can have is 7 years elapsing. Everybody okay with that? Okay. So now let's go to the y min and max. So the y here is representing n, or the number of computer viruses. What is the smallest number of computer viruses we can have using this model? Not 0. It's considerably more than 0. Annalise?
Like the first, n equals 573. That one is like x, and then n equals 125,000 is.
X is t, y is n.
How do you know like where you're looking for when you change it to y minimum to x?
So y is n. That's the number of computer viruses, right? So think back to the question. What is the least number of computer viruses I could have?
What is the original story?
2,500.
Great. In the interest of making that a round number, I'm just going to use 2,500, a little bit less than that. Everybody okay there? What do you think a good value for the maximum number of computer viruses we could have is? How long is this model good for? We just answered this. 7 years. What did we do in part B? We found the number of computer viruses there would be 7 years later, right? So let's use that answer for our y max. Now, rather than typing all those in the interest of just making it a round number, I'm just going to make it 250,000. It's kind of close enough. Is everybody okay there? So here I didn't even have to make a guess. If I didn't have that answer to part B, what would my guess, what do I know about the guess for the y max? What does it have to be bigger than? Think about the question we're trying to answer, specifically for part C. Exactly. It has to be bigger than 125,000 because that, the question we're looking to solve is when is there 125,000 viruses. All right, now that we've done that, we're ready to hit graph. So here this curve is the exponential growth function, and this straight line is my 125,000. So the point that I'm looking for, the intersection, is right there where my arrow is, right? Let's have the calculator find that point for us now. So to access the menu of options that I can use on a graph, I can press second and the trace button. If I look at this list of options, which one sounds like the one we need? Intersect. So let's scroll down and select the intersect command. If I look at my picture now, the calculator is asking some questions here. First curve. You also notice that there's a cursor now on my function. So this is one of the two functions I want to find the intersection of. So anywhere on here, I can press enter. So that spot looked fine. You'll notice now that my cursor is automatically toggled to the next curve. So I want to find the intersection with this straight line also. So now it says second curve. I'm on the straight line. So I'll press enter again. And then it says guess. So I'll just use my left and right arrows to scroll my cursor over to where it's close to that intersection. That looks good. And I'll press enter again. Now what the calculator says is the intersection is at x equals 5.95 yada 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 and y equals 125,000. So remember that x on our calculator represented what variable in our equation? T. So I know t is about 5.95 years after 1996. Everybody okay with that? So the calculator did all the hard parts for us. We just had to know how to get our calculator to do that. Annalise?
Why did you click it 3 times before scrolling close to the intersect?
Well, the first question is 2 questions. Ask the calculator needs to know what 2 lines it wants to find the intersection of. Because you could have 2, 3, 4, 5, 10 lines on your graph all at the same time. And you only it can only find the intersection between 2 of them. So you just have to tell it which 2 lines to look for the intersection on. Now we only had 2 lines graphed, so really all we have to do is start by pressing enter twice and then move close.
You just enter anywhere?
Yeah, anywhere on, if it's on the curve that you're interested in, doesn't matter where it is.
Oh, but kind of on that.
It has to be on the 2 things you're interested in finding the intersection of. Doesn't have to be close to the intersection. Just has to be on the 2 things, what 2 things am I using? That's what it has to know first. And then where is it close to? And then that's it. So it's not a hard function to use, right? What do you guys think about that? Well, just because it's doing it the first time. Once you're good at it, it just takes a couple of seconds. It's, at least writing-wise, there's not a lot to write down, right? There's not a lot of steps and things to keep track of. Vitalik, or Massimo. Sure. let's do another example here. So it says, oops, you buy a new snowmobile for $4,200. The value of the snowmobile decreases by 10% each year. We want you to start by writing an exponential model for the snowmobile M T years after its purchase. So again, there's nothing to do with banking here. So we'll use kind of our general growth and decay model. What are we going to in Y? M. Good. That's the future value of the snowmobile. What's A?
Present value.
4,200, the present value of the snowmobile. Very good. AKA the purchase price, right? What are we going to put in for R?
20.
So the rate of change, which you said was 10% or 0.1, that's close. Read the question there a little bit more carefully. Negative 0.1, because it says decreasing. Yeah. So the words in the story problem definitely matter. So is this growth or decay right here? This is decay. And then we have a T, right? Everybody happy with that? Okay. So my next question is, what is the value of the snowmobile in 3 years? So to do this, we're going to use our exponential model that we just built. Which value are we looking for, M or T? M. Okay, so to find M, we need to fill in a value for T, which would be what in this case? Okay. Everybody should be clear as to where we got the 3 from, right? Okay. So I'll just type this into my calculator then. One plus negative 0.1 is 0.9. Okay. So there we go. There's my value of my snowmobile after 3 years. Yes. Yes. So our next question says, when is the snowmobile worth half of its original value? So again, we'll start with our model that we made in the first part. In this case, which are we looking for, M or T? T, how do you know? When is a time question, right? Okay. So to solve for T, we need to know what M is. What is M going to be in this case? $84,000. No. Remember, what's going on here? Is this growth or decay? Is this growth or decay? Decay, right? So should the value of the snowmobile be going up or down? Down. So the value for M cannot be more than the purchase price, right? Since it should be getting less. So 84,000 is not a good guess there.
And then 4,200 would just go up, right? But I just read the dollars.
Okay. What should be our value for M here? Read part C again. Read the words. 2,100. That's correct. How'd you get that, Jack? It's half of 4,200. That was the original value of the snowmobile because it was the purchase price. Everybody good there? All right, let's go to our calculator. So I'll go to the y equals menu. I'll type in my model in one and then the 2,100 in the other. Everybody okay with that? Next, we have to set a window. So again, x is time, so 0 is a good minimum time. The x max, do we know what that's going to be specifically? Or know what that should be specifically? Not really, right? In this question, we weren't given like for the next blah, blah, blah years it does this. So we're going to have to take a guess here. What's a decent guess? What's a guess? Like 1, 100, 10,000? 50? Who here has ever owned a snowmobile before? Your dad has a snowmobile. How old would you estimate your snowmobile is? 15 years. Great. So let's put 15 there. Okay? That's a reasonable age maybe for the age of a snowmobile. Somebody has one that's still kind of... He's had it for a long time. Well, 15 is probably not a bad guess as an upper bound for this. Probably you don't own a snowmobile much longer than 15 years unless you're just like barely using it. But that's fine. But not a bad guess. The Y minimum. What would be a good value for this? 5? Why 5?
Well, what if you have it for like 3 years, then you move, and then you realize you sell it? Like after those 2 years, you have. I don't know. No one else is saying anything.
So no, I'm curious as to but why 5 though. So remember, what's going on here? Is this growth or decay? Decay. So what's the least value a snowmobile could have? 0. So let's use that as our Y min. That's why I was curious about 5, because it was actually a reasonable answer. I just wanted to kind of pick why 5. But yeah, basically the snowmobile, worst case scenario, is worth nothing, right? Can't be negative. What's the most value the snowmobile will have? 4,200. Whatever you paid for it. It's not getting more valuable after you drive it off the lot.
In mine, it's like a rare snowmobile.
Well, not if you're using it regularly even. Even if it was a rare snowmobile, if you've used it like thousands of miles, it's not going to be worth more than it was. All right. Plus, I don't think there's a big collector's market for snowmobiles. You never know. You're right. Okay. So here's our picture. And we made some good guesses, right? We can clearly see the intersection. In reality, when we're picking these X mins and X max and Y min, Y max, all we really need to do is be able to see our intersection, right? So what's a good value for the x min, x max, y min, y max? It's numbers where I can see where the two lines cross. As long as I can see where they're crossing, I picked good numbers. Now you can think about it a little bit and probably be pretty sure you're going to get the intersection than if you just like write some stuff down. But, you know, all right. So let's find the intersection then. So I'll press second trace, pick the intersect command, first curve, second curve, and then move over by my guess. And I get 6.58. So I'll say after about 6.58 years. We okay there? All right, we'll do one more example. Okay. So you deposit $4,000 in a bank account that earns 2.92% interest compounded quarterly. First question we ask is how much is the account worth in 5 years? Which model should I use? Yeah, this one is definitely about banking. So let's use the compound interest model. Okay. What does FV stand for? Future value. What are we looking for in part A? A future value, so we don't change that at all. What's PV? Present value. So how much money did we start with? 4,000. Okay. What is R? Interest rate as a decimal. So in this case, it would be not 0.29, 0.0292. Right? What is N? Number of compounds per year. So what is N in this case? Andrew says 4. Where'd you get 4 from? Quarterly. Quarterly would mean 4. And then T is the number of years. In this case, T is going to be 5. So I'll just plug this into my calculator then and see what we get. So, how should I round this number? Where should I round this number at? No, I wouldn't do that. I would round it to the 100th. Why the 100th? It's money, right? So we should round to the penny. Everybody feel good about that? Okay. So, last question. How long until the account is worth 10,000 monies? What are we looking for? How long? T. Okay, so what are we going to plug in for future value to find T then? 10,000. Okay, so let's get this into our calculator. Okay. All right, so we did that. Again, T or X is time in our case, so 0 is a good minimum. Maximum. We have 4,000. We want to end at 10,000. Is that going to take a little bit of time or a long time? Probably a long time, right? Let's pick a big value for T here. What do you think? 100? I don't know. I'm guessing. I usually like to overestimate that. What's the minimum value for this bank account? 4,000. And the maximum, I'm going to pick something bigger than 10,000 so I can see it, where the intersection happens. So I maybe pick 12,000 or something. I just want to pick something bigger than 10. So there's my compounding interest curve. And here is my 10,000 curve. So there's my intersection right there. So second, trace, intersect, enter, enter, enter. And it happens after 31.49 years.